Hey everyone. So, discuss briefly. Already we have discussed on what is self-inductance and mutual inductance also, right? Few more points we'll see. We'll discuss about those. Okay guys. So first 2 minutes let us try to recollect back briefly what we have discussed about self-inductance and mutual inductance. Okay? Reduce the speed. Reduce the speed of the fans. Right. Yes, guys. Self-inductance. What is self-induction and what is self-inductance? Self-induction is a process or phenomena of inducing EMF in a coil due to its own current, due to the current in the coil itself, its own current is called self-induction, and it is observed that the flux linking with the coil depends on its own current. It is said to be proportional to current in the coil. So it is expressed as phi is equal to a constant L into I, where L is called coefficient of self-inductance, coefficient of self-induction or coefficient of self-inductance or simply self-inductance. Right? It is given as L is equal to phi by I. From this you can discuss the units and dimensions of this. As EMF induced in the coil is equal to minus d phi by dt, we have also discussed that if we take this phi as Li, right, minus L into di by dt. Using this we can write L is equal to minus E by di by dt. So these are the points discussed briefly about self-inductance of a coil. Whereas self-inductance of a flat circular coil, self-inductance of a circular coil, L of flat circular coil, if you consider this is a circular coil of radius R and the current I is flowing in it. It produces a magnetic field at the center, and if it is having radius R, then the area of the coil is given by pi r square. Then we can say magnetic field produced is mu naught I by what? 2R if the coil is having one turn. Okay, so then due to n number of turns, magnetic field, if it is having n number of turns, magnetic field is n into mu naught I by 2R. Whereas the flux linking with this coil due to the current in these terms is given by phi is equal to what? Usually phi is equal to BA. It is the number of turns, it is n into BA. So this gives, can also express this as what? Final expression you can take directly. So mu naught n square or mu naught n into n square I by 2r into a, or if you take it as a as pi r square mu naught n square. Here r gets cancelled, r I by 2, and by comparing this with phi is equal to Li, you can write self-inductance of this circular coil is nothing but L is equal to mu naught n square r by 2. Thus, it is mu naught n into mu naught I by 2r, and this r and 1r in this area is cancelled, here is 1. So this is for circular coil, flat circular coil. Whereas the self-inductance of a solenoid. So what is self-inductance of a solenoid? Have you copied all these points or not? Self-inductance of a solenoid, L of solenoid is directly, can you recollect back what is this? L is equal to mu naught n square, small n square, pi r square, that's it, pi r square L, pi r square L, or you can write it as AL, mu naught n square AL in terms of small n, right? So this is what we call self-inductance of a solenoid, right? And we have also discussed about what is mutual induction and mutual inductance. Mutual induction is a process of inducing or process of producing induced EMF in a secondary coil due to change in current in the primary coil. The figure, if you remember, if you have this primary coil connected to a battery and a plug key. So if it is closed and the current I flows because of this current in the primary coil, if you have another secondary coil, it is connected to a galvanometer, you can observe that a deflection is showing, means EMF induces and hence current also induces in that. So here, due to the current in this, it produces magnetic field and hence magnetic flux will be linking with this. Magnetic flux will be linking with this. That flux linking within the secondary coil, flux linking the secondary coil, you can see it is mutual. Discussing about mutual induction or inductance. Is flux linking with the secondary coil is proportional to current in the primary coil. Current in the primary coil. So from this we have expressed phi s is equal to m into I into P. M is coefficient of mutual inductance or simply mutual inductance or coefficient of mutual induction, right? So this can be expressed as the same way as L is equal to phi s by IP, and you can also write here also the induced EMF is equal to minus d phi by dt. EMF induced in secondary coil is equal to d phi in secondary coil by dt. So you can also write it as minus m into d in what do you call flux in secondary coil is depending on the current in the primary coil. So it is VIP by dt, and this you can also write m is equal to minus e by what dip by dt. So this is another way of calculating mutual inductance or in general any coil. Whereas mutual inductance of two coaxial solenoids. So this I hope you guys are recollecting back all these points. Try to write and remember, try to recollect back all these points. So first 5 minutes, we are not wasting this, okay, so that we can recollect back. Okay. So mutual inductance of coaxial solenoids. M of coaxial. This part in the need guys to have to copy this. I hate you for students who are discussed already. Mutual inductance of coaxial solenoids. So if you have a core on this if we wound a coil, or we call it as a solenoid of n1 number of turns. So we call this as you say a solenoid S1. If you wound the coil of solenoid S1 on the core, which is having length L, small l is used, so that if N1 is equal to number of turns per unit length of the first solenoid, number of turns per unit length, number of turns per unit length, and similarly if you turn another coil, we call it as, if you consider another solenoid having n2 number of turns, then where n2 is total number of turns in secondary solenoid on same length L, the number of turns in secondary coil per unit length gives you small n2, number of turns per unit length in the secondary solenoid. Number of turns per unit secondary solenoid. If n1 is this and n2 is this, and both are having same area because they are wound on the same core, if they are both are uniform, wound on a uniform core having same area, then you can express and you say if a current I is passed through the primary coil, this produces magnetic field. So magnetic flux linking with each turn of secondary coil is equal to magnetic field due to the primary coil into area. Magnetic field in primary coil into area, where magnetic field on the axial point of a solenoid can be expressed as mu naught Ni, mu naught n small n, can say primary coil N1 I into area. Area is the same for both. Whereas this is flux linking with each turn. For n number of turns, if you want, you can also express this as capital N1 by L. Have a note of this, quick note of this. So you can also write small n1 equal to n1 by L, capital N1 by L. So you can write it is equal to mu naught n1 I A by L. This is flux linking with each turn of secondary coil due to the current in the primary coil. Current in the primary coil you can take it as I1, or you can take it as I. Whereas flux linking with the total flux linking with the secondary coil, the whole solenoid having in the secondary coil having n2 number of turns is equal to n2 into B1A. N2 into B1A. So here you can also write it as it is equal to mu naught N1 N2 I A by L. This gives the total flux linking with the whole secondary solenoid. Now, if you compare this total flux in terms of, because of the current in the primary solenoid, flux is linking with the secondary solenoid, and hence EMF is inducing in that. That is called mutual induction. So you can express this is equal to M. The induction produced in secondary coil due to the current in the primary coil, you can write it as M21 into what? M is proportional to the current. So M2I. So if you take this is 1, this is 2. By comparing this, we can say M1, 2 or M2, 1. Even you can take, instead of sending current in the primary solenoid, if it sent in secondary solenoid also, you get the same result. So this we call it as coupling, or you can say mutual inductance. Coefficient of mutual inductance is equal to mu naught N1 N2 A by L. So this gives the coefficient of mutual inductance, or simply you can say mutual inductance of the secondary coil with respect to first, or the first coil with respect to second. Both will be same. So it depends on the, here if it is the coils are in free space, mu naught will take. If it is on some another medium, depends on the medium of the core, and number of turns of the primary coil and secondary coil, and area and length of the solenoid. Got it? So it does not depend on on which solenoid current is flowing. Instead of considering the first one is primary coil, second one is secondary. If you take second one is primary coil and first one is primary also, the same result will get. So this point you have to remember. So as a conceptual point, based on this also you may come across some questions. So this is briefly about mutual inductance of coaxial solenoids. Area of both solenoids is same because this are bound on the same core, having same area. Same area. Here we are considered even length of the solenoids also same. Alright. Next, we'll see briefly what is energy stored in a solenoid. Let's note down. Energy stored in a solenoid. Energy stored in a solenoid. Yes guys. Energy stored in a solenoid. It is what does this mean? Energy stored in a actually instead of saying this solenoid, it's energy stored in an inductor. We call it as inductor. The solenoid will have some self-inductance. If single solenoid will have, if the value self-inductance of a solenoid is a larger value, then solenoid can be treated as an inductor. So both are same only. Solenoid and inductor both are same, right? Provided self-inductance will be having some predominantly larger in value. That's it, right? So now, in case of an inductor, how can you find the energy stored? Energy stored. Usually, to find energy is nothing but work done. Okay? So you have to say before this, can you work out few questions? Then we will discuss this, and some one or two simple questions are there based on this. We will work out those also. Let us see first one or two numericals based on these first. Then we will go ahead with the energy part. So, do you have volumes, everyone? So go through. Yes, guys. Level 2, exercise 1. Level 2, exercise 1. Right. See here. Question number 16. Right. Level 2. Exercise 1. I want first entire class to be completely quiet. It's not time pass session. Level 2, exercise 1. Question number 16. Question is, an EMF induced in a secondary coil is 10,000 volts. EMF induced in a secondary coil is 10,000 volts. Then current breaks in the primary. Breaks means stops. Till then it was current was flowing. Already done? Okay. So question number 17. We will do question number 17. Okay. Then we will see question number 17 is, the question is, a mutual inductor consists of two coils X and Y as shown in figure, in which 1/4 of the magnetic flux produced by X links with Y, giving a mutual inductance M. What will be the mutual inductance when Y is used as the primary? So this is there is no calculation is involved in this. This is just directly conceptual question. Just now I have discussed. If you pass current I in the primary coil, EMF induced in the secondary coil, so that mutual inductance of secondary due to current in primary should be equal to mutual inductance the primary due to current in the secondary. Both are equal. Any coil if you treat as primary or secondary, same mutual coefficient of mutual inductance will be same. Is it clear? So if mutual inductance if mutual inductor consists of two coils X and Y as in figure, and if 1/4 of magnetic flux produced by X links with Y and giving mutual inductance M, means under the same conditions, if you treat Y as primary, X as secondary, you have the same mutual inductance. Okay? So mutual inductance in this will be same, M. Got it? Next. Question number 18. Question number 18. This is also a formula based one. Let us see here. A long solenoid of length L, cross section A, having N1 turns, has wound about its center. A small coil of N2 turns as shown in figure. The mutual inductance of two circuits is again, look here. So what is this? A long solenoid of length L, I have taken it as L here, is and having a cross sectional area of A, having N1 number of turns, now has wound about its center. Since this is about the center, it is wound, provided. Now, has wound about its center, another small coil of N2 turns, N2 will be different than N1, as shown in figure. The mutual inductance of these two coils is, so mutual inductance between any two coils is, if they are having N1 and N2 number of turns, it is given by mu naught N1 N2 A by length L. Got it? So you can say here mu naught N1 N2 A by L, which gives the relation mu naught N1 N2 by A. So N1 N2 A by L. Second option is the right one. This is not a calculation based one, conceptual based one only. Next, you see question number 19. So for this is actually M is equal to what? Mu naught N1 N2 A by L. Like the same formula based conceptual based question. Then question number 19, it is given that, what is this? A small coil of radius small r is placed at the center of a large coil of radius capital R, where capital R is much greater than small r. The two coils are coplanar, both are placed in same plane, coplanar. Then the mutual inductance between the coils is proportional to. So you can consider this like this. There is a small coil with a radius small r, right? And another larger coil, go down. Another larger coil of radius capital R, and both are placed in same plane. They are coplanar, right? Provided, what else is given here? capital R is much greater than small r, or small r is much less than capital R, right? Then the mutual inductance between the coils is proportional to what? Means when the current I is flowing, what is given here? A coil of small coil of radius R is placed at the center of a large coil of radius R, which is where capital R is much greater than R. The two coils are coplanar. So what we have to understand is, provided if a current I is flowing in the outer coil or larger coil, then coefficient of mutual inductance is proportional to what? Is the question. Got it? Actually, it has to be given clearly that when a current I is flowing in the larger coil, it has to be given clearly. Right? So you have to understand in this case, but usually in normal exams, everything should be clearly mentioned. It is not like hidden data will not be given. Now, in this case, what is the coefficient of mutual induction? Induction only, the mutual inductance between the coils is proportional. We know due to the current in this, it produces a magnetic field at the center. Magnetic field. So B is equal to what? Mu naught I by 2 into capital R. Yes. Yes or no? And the smaller coil is placed inside this, at the center of this. So, because of the current in this, the flux will be linking with this coil. And flux linking with the secondary, this is a primary coil, you can say this is secondary coil here. Flux linking with that secondary coil is equal to what? Is equal to B into A. B into A. This B due to the primary coil into area of this. Area of secondary coil. B field due to the primary coil into area of the secondary coil. This is clear? This is equal to, you can say, mu naught B1 is what? Mu naught I by 2R into area of secondary coil is pi R square. Did you understand? Now, this is the total flux linking with this secondary coil. Whereas total flux in terms of mutual induction is given as phi S is equal to M into I in primary coil. That is first coil. Whatever it was. Got it? So here this current I is primary coil, current in primary coil. So if you compare this, you can write M is equal to mu naught or pi mu naught R square by 2R is coefficient of mutual inductance. The question is, mutual inductance is proportional to what? Here pi is a constant, mu naught is a constant, 2 is a constant. So here the mutual inductance depends on the radius of this and radius of this. So if you keep all these constants, you can say it is proportional to R square by capital R. Right? So this is the relation which is suitable for the given question. So what is the one? R square proportional to R square by capital R. Right? Next, question number 20. Right? I'll wind up in just 10 minutes. And again, Sir will take. We need to cover few questions and concepts. Question number 20. Question number 20. So what is given here? It is given that the coefficient of mutual inductance of two circuits A and B is coefficient of mutual inductance of two circuits A and B is 3 millihenry. What is this coefficient of mutual inductance? M is equal to 3. Milli means small m. Small m h means millihenry. Milli means 10 to the power 10 to the power minus 3 Henry is SI unit of coefficient of inductance. And the respective resistances are 10 ohm and 4 ohm. So the resistance in the first one is 10 ohm and that in the second one is what? 4 ohm. Coefficient of mutual inductance of two circuits A and B. And how much current should change in 0.02 seconds in circuit A? So what is this? dt, small change, time dt is equal to 0.02 seconds in circuit A, so that the induced current in B should be 0.006 amperes. Induced current di, small current in the secondary circuit, this is in secondary circuit is equal to 0.006 ampere. What is the question? How much current should change? How much current should change in 0.02 seconds in A? Oh, what should be di1? So that the induced current in B should be induced current in secondary coil. You can say I2 will be this much. This is the question. Yes, by using this, how can you do it? So what is given? Induced current usually should be equal to induced EMF by resistance. So we have to find induced EMF by using mutual inductance relation. Can you try? So try yourself. Try to draw the pictorial representation for two coils and try. Take a minute. I give you exactly 1 minute. Try yourself. Try yourself. What is flux link? Actually here what is given here? What should be the change in current in the primary, so that induced current in the secondary is this. Induced current in the secondary is this. So you know, flux linking with the secondary coil is proportional to current in primary. Right? So whatever you know, the points, the conceptual points, use and write one by one and apply this. Try yourself. Let's take a minute. It is not just to write, sitting here and writing whatever is happening on the board. You have to be here, body and mind should present here and think. Yes? Very fast. Finish this, we will discuss briefly about energy stored in inductor. Then we will wind up. Fast. One question we will do based on that. Not many. Just finished. Yes. What should be the change in current in the primary, so that induced current in the secondary is this. Now what is EMF induced in secondary coil? E is equal to M into di by dt. Induced EMF is this. This is change in current in the primary. Primary is equal to EMF induced in secondary. Right? You can write it as 1 and 2 subscriptions. From this change in current in the primary, you are asked to find di1 is equal to d2 into dt by m. Here dt is given the time in which they are supposed to change, m is also given, e2 EMF induced is given, resistance is given, and induced current is given. So induced EMF, can you find? Because induced EMF in this secondary is equal to what? Or you can say induced current in secondary is equal to induced EMF in secondary by resistance in the secondary. Yes or no? From this, can you write E2 is equal to I2 into R2? E2 induced EMF is equal to induced current. This is nothing but I2 is given, R2 is given. So both are given. By using this, can you find E2? And hence can you find out this? That's it. Let's do it. Do it. Finished? What is the answer? 0.16. Options 0.16 ampere. So it is equal to 0.16 ampere. Changing current in the primary. Right? Now let us see briefly what is that. On the last concept, energy stored in an inductor. We'll see briefly what is that, and only one numerical based on that we'll see, we'll discuss. Then I will wind up. Write down energy stored in an inductor. Energy stored in an inductor. Energy stored in an inductor. Inductor. Right? Inductor is nothing but a coil. Inductor is nothing but a coil. If you consider a coil which is connected to a source of EMF. Yes, very good, superb, nice. It is connected to a source of EMF E, and a current passes through it. EMF produced in the coil. EMF induced in the coil. So induced EMF, you can take it as E is equal to minus L into di by dt. Take this one. EMF induced into current in the circuit. The EMF induced is this. We have this one simple point here. It is minus L into di by dt is induced EMF into I. Into I. This you can write as L minus L I into di. So now the total burden in transporting this charge is given by integral of dw. It is equal to minus integral of L into integral of I di. As I is the variable, you can take it as actually speaking, in an inductor current grows when you have a key here. If you close this, the current immediately will not become maximum. It grows from zero value. So that means we are changing the current. To do that process, we are doing some work. The rate of doing work to grow the current from zero value to the maximum value or steady value is this one. This is nothing but the power. That we are taking it as dw by dt. So So this can be taken as, whereas if you close it, it starts increasing from 0 to maximum value. Whereas if you break the circuit, then from maximum value it decreases to 0. So on the circuit, off the circuit, or break the circuit, make the circuit. If you make the circuit, the current starts increases from 0 to maximum. Break the circuit, current decreases from maximum to 0 value. So this terminology you have to remember here. When you make, if you consider, then that what you call the work in increasing or in the growth of current is given by this is equal to minus L into integral of IDA is nothing but I square by 2. I square by 2. So you can also write this as W is equal to here this only the the magnitude of organ if you need, then you just don't worry about that sign convention is equal to half L I square. This work done in growing the current from 0 to the maximum value will be stored as energy in the inductor in the magnetic field. So you can give it this as U is equal to half Li square is equal to half Li square. Right? This is called as energy stored in an inductor. So it is directly proportional to current square for a given inductor. So for given inductor, L is constant. So it depends on how much current we are allowing to flow. If the source changes, current changes, energy stored will changes for a given inductor. Right? So this is a simple relation you have to keep in mind. Now let us see one simple numerical based on this. Then we write up. Sum it down. Question number 15. See, question number 15 and 11 to exercise 1. Right, guys. It is given that there are two batteries A and B having same EMF. A has no internal resistance and B has some internal resistance. An inductance is connected first to A, and the energy in the uniform magnetic field set up inside is U. It is now disconnected from A and reconnected to B. Now the energy stored in the uniform magnetic field will be energy stored. We are asked to find in these cases. So what is given and what you are asked to find. So how to relate the given data. So let us see once again quickly. If you go through the question, what you can understand, there are two batteries A and B having same EMF. Same EMF. This is one battery, this is another battery, A and B having same EMF. This is having zero internal resistance, this is having some internal resistance, non-zero internal resistance. Non-zero internal resistance. Provided if as A has no internal resistance and B has some internal resistance, now inductance is connected to first to A. So inductor is connected to this A first, having say coefficient of self-induction N. Then energy stored in the magnetic field of this is U. U is energy stored. You know U is equal to half Li square. For a given inductor, L is a fixed constant, so you can say it is proportional to what? I square. But in case of inductor, I is what? Induced current. Induced current is equal to what? E by R. Means EMF, net EMF by total resistance. So net EMF is E. Total resistance in this case is nothing but there is if the coil is having some resistance, we have to take this as the resistance of this coil, provided internal resistance is 0. Got this? Whereas now once you disconnect this and connect to this secondary one, same coil having inductance L, resistance R. The question is Now what should be the energy stored? Let us say U dash is proportional to, or you can say how can we compare this with the initial energy stored? Here this is also proportional to I square, but in this case it is you can say it is nothing but E by R. Whereas in secondary what is that? In case of second battery, I is nothing but E by resistance of the coil plus internal resistance. As resistance in the denominator increases, I will decrease. As it is proportional to I square, you can say this is I dash square. I dash is lesser than what you can say. As this is less than I, you can say U dash will be less than U. Is it clear? As I dash is, because I dash is less than I, you can say U dash will be less than U. Simple relation. Right? Okay. Let's go through this as already it is 9. I'm winding now. So for this weekend portion, try to practice the same questions and the previous exercise also the similar kind of questions. And now itself I am giving that the next week portion is the entire chapter of EMI. Again we will revise this. So if you have any confusions, okay, you can revise once again the same chapter. Okay, so try to come out of those confusions.